3. So welcome to Math341 probability. This is lecture 9, and today we'll be talking about sums of random variables, moments, and special distributions. So because the CDF method is so important, I want to do at least one more problem and just talk a little bit about how do you use it in practice. The high-level reason as to why we care so much about this is if you have one way of generating random variables, say a uniform random variable, you can then use this to generate other types of random variables. So the question becomes, do we have ways to generate, say, uniform random variables? Can you do something with perfect randomness? And that is a really interesting problem for the computer scientists. We have a lot of things that are close, but how close do you have to be? I'll talk a little bit about the Cauchy distribution as a little bit of a non-standard distribution and a nice way to review some of your calculus. And then talk a little bit about joint probability density functions. Right now we've been looking at distributions that are functions of just one input. Or you might have something that's a function of several inputs. How do you handle stuff like that? I'll talk a little bit about one of my favorite results in probability, linearity of expectation. That for a lot of things, the expected value of a sum is the sum of the expected values. Anything that sounds like this is exactly what you would want to be true in life. The derivative of a sum is the sum of the derivatives. This is the type of rule you would love. Anybody remember the product rule or the quotient rule? Right. If you were creating calculus, this is probably not what you would choose for the product. It turns out it has to be that way. That's the only thing that's consistent, but it's a lot more work to use. We don't have linearity for the variance. The variance of a sum is not always the sum of the variances, but it is true for expectation. And then if there's time, I'll talk a little bit about Buffon's needle. So the big thing today is the power of linearity and whenever possible, trying to avoid brute force computations. It's nice to know that you can solve a problem by brute force, but in practice, you hate to do that. Now, if you can have your computer churning it out in the background, that's one thing. But if it's you who's actually spending the time, we talked about the numbers 1 through 9 and forming the fractions. You can solve that by brute force. But if you had to physically do the calculation yourself, you'd go crazy. Are there things you can do to prove where some of the numbers might be to cut down on the calculation? Okay, so let's start with a review of the CDF method. So let's let y be x squared, and x will be a non-negative random variable. So this means that x only assigns positive probabilities to, say, 0 and up on the real line. So the probability that x is less than 0 equals 0. The last time we did this, we said that x was a uniform random variable on 0, 1, and we used the CDF method to calculate the probability of y. And we did it by explicitly integrating. And again, I know as soon as class is done, you deal with the rest of your stuff for the day, and then you go home and you pore over the notes, intently for hours. You have chat groups, DMs, all that stuff. And I'm sure some of you realize, wait a minute, we spent this time in this brute force calculation, we integrated, and then we immediately differentiated the result of the integration. This seems foolish. It worked, but there was no need to do that. So let's revisit this problem, and let's integrate without actually doing the integration. So we're going to let y be x squared. X is a non-negative random variable, and we want to calculate the probability that y is at most y. So this is the probability capital Y is at most lowercase y. Well, since y equals x squared, this is the probability that x squared is at most y. So really, it should be minus the square root of y is less than equal to x is less equal to y. But since x only takes on, 0 or positive values, do I really need to worry about the square root of y? So for those who are coming in late, if you have class beforehand, let me know and we'll adjust a little bit when we start classes. We're just doing the CDF method from last time, but we're doing it without doing the brute force integration now. And we're assuming we have a non-negative random variable just to make things nice. So the probability that it takes on a value less than 0 is 0. So do I really have to look at x between negative root y and y? No, I can just assume that this is the same as the probability that capital X is less than or equal to the square root of y. Now, what is the probability that x takes on a value at most square root of y? Well, this is the CDF of the random variable x. And we evaluate it at square root of y. So think of it as the CDF of x being at most little x, which would be the square root of y. And this is where it's useful to have lots of subscripts. So this is capital F sub x, the cumulative distribution function associated to the random variable x, evaluated at the square root of y. Well, we know that the probability density function is the derivative of this cumulative distribution function. So we showed the PDF is the derivative of the CDF. So if we take the derivative of both sides, I'm going to just write it very slowly, d by dy. Okay, so the left-hand side, the derivative of that is just the probability density function, f sub y of y. Now I need to take the derivative. Anybody want to tell me what the derivative of the bracketed quantity is? What rule should I use to take that derivative? Chain rule, excellent. How would you say the expression in the bracketed quantity? How would you say? Just speak to me. How would you say the text inside the bracketed quantity? It is no. Good. The PDF or f sub x of the square root of y. Whenever you hear of, think chain rule. So there's an of here. I really have a composition of functions. So if I have a of b of x, and I want the derivative, that's a prime at b of x times b prime of x. That's the chain rule. I have an of going on here. So what do I have? Well, I have the derivative of the first function evaluated at the square root of y times the derivative of the square root of y. Well, what's the derivative of capital F sub x? Lowercase. So notice we never actually had to calculate what the antiderivative was because we immediately take its derivative. So even though we were able to in the previous class, there was no need. Now that allowed us to avoid having to take the derivative of the square root of y like this. That's fine. But the whole point of the CDF method is you don't need an explicit form of the antiderivative. And that's why this method is so powerful. Now I need the derivative of the square root of y. That's y to the 1/2. So it's going to be 1/2 y to the minus 1/2. So do not need a closed form expression for the CDF. And that's what makes this method so powerful. Okay. So you can apply this now to a bunch of similar problems. The key thing is to always remember that you've got a chain rule going on. We have capital F, capital X evaluated at the square root of y. And we have to remember that when we take the derivative, we have to take the derivative of the square root of y as well. As a check, if you didn't put that in, if you then tried to integrate it, if you didn't have that derivative of the square root of y, it would not integrate to 1 typically. Okay. So let's move on to one of my favorite distributions, the Cauchy distribution. Out of curiosity, how many of you have seen this distribution before? No one has seen this before. Okay. So this is one of my favorite techniques, the method of divine inspiration. Let's review trig. Okay. So we just did the chain rule a moment ago. So one of the most useful applications of the chain rule is imagine we have two inverse functions. So imagine f and g are inverses. So a of x equals f of g of x is x. Then what would a prime of x be? I'll accept two answers. So f and g are inverse functions. F of g of x is x. What's a prime of x? Good. So that's one acceptable answer is you use the chain rule. And there's another acceptable answer. It's also just one because of the derivative of x. Therefore, g prime of x is 1 over f prime of g of x. Why is this important? If I know the derivative of f, I can use that to get the derivative of g. You might have seen this in a calculus class to pass from the derivative of e to the x to the derivative of the natural log. So consider the tangent of the arctangent of x. What is the tangent of the arctangent of x? X. I take the tangent of the angle whose tangent is x. What is the tangent of the angle whose tangent is x? It's just x. So this means tangent and arctangent are inverse functions. Some people do tangent to the -1 to indicate the inverse tangent. The danger with that is always, is that the inverse function or is it 1 over? And this is one of the reasons why we often say things like arctangent. So this implies that tangent prime of x is 1 over arctangent, I'm sorry, is 1 over, sorry, arctangent prime of x is 1 over tangent prime at arctangent of x. How many of you remember calculating the derivative of arctangent all those years ago? Okay, okay, one person. Okay, oh, I should probably put my hand up too. Not that many. So, who remembers the derivative of tangent? The derivative tangent is sine over cosine. So tangent of x is sine of x over cosine of x. How would we take the derivative of that? What would we use? Quotient rule. So the derivative of sine is cosine. So you get cosine x minus sine x, and the derivative of cosine is minus sine x over cosine squared of x. The numerator is just cosine squared x plus sine squared x is 1. So you get 1 over cosine squared of x. Anybody remember what 1 over cosine is? Yeah, I hate this. So, when I become supreme deity, which is almost surely not going to happen, one of the things that's on my list to reconsider is having cosine and secant linked and sine and cosecant linked. If you go through and understand the language as to what is a coangle, it makes sense. If you don't know that, it seems absurd that 1 over cosine should be with secant and not with cosecant. It's how it is. Okay, so we know the derivative of tangent is 1 over cosine squared. So that means arctangent prime of x is 1 over tangent prime, so it's going to be cosine squared arctangent of x. Does that make any sense to anybody? The cosine squared of arctangent of x, does that look like a function you know? Okay, doesn't look like anything reasonable to me either. And I promise you there is a reason we're doing this. Let's draw a picture. I want an angle whose tangent is x. Tangent is opposite over adjacent, right? So how should I choose the sides so that the tangent will be x? What should the vertical segment have length? X. And horizontal? So that's the simplest way to construct a triangle with an angle whose tangent is x. So here theta is arctangent of x. What's the hypotenuse going to be? It's a right triangle, right? So it's just the square root of 1 plus x squared. So cosine of arctangent of x is just 1 over the square root of 1 plus x squared. So cosine squared of arctangent of x is 1 over 1 plus x squared is arctangent prime of x. Okay, so this is just calculus. Everybody here should have taken at least 3 calculus classes as an ante to get into this course. Wouldn't it be nice to use some of the material you've learned or should have learned? Right. So the most important part here is that if we have inverse functions, if we know the derivative of one, we know the derivative of the other. It is very hard to have functions that have nice explicit integrals. We just found a function that has a nice integral. What is the integral of 1 over 1 plus x squared? Arctangent. Okay. So 1 over 1 plus x squared, this function, it's going to have a finite integral if we go from minus infinity to infinity. It decays rapidly enough. And so now, let's go to the Cauchy distribution. So there's 2 ways to do this. I can either write down the Cauchy distribution directly, or I can write 1 over 1 plus x squared. We can integrate it, and then we can see what we need to fix it with. Given that I've taught this class for, oh good God, over 2 decades now, I'm going to just write down directly what we should look at. All right, let's study f of x to be 1 over pi, 1 over 1 plus x squared. I'm putting in the 1 over pi because I know what the answer is. If I didn't put in the 1 over pi, I could study 1 over 1 plus x squared, and I would see it's non-negative, and it integrates to a finite number, and then I would just renormalize. So this is non-negative. Does it integrate to 1? So if we integrate from minus infinity to infinity of 1 over pi, 1 over 1 plus x squared dx, do you agree that this is just 2 over pi integrating from 0 to infinity, 1 over 1 plus x squared dx? The function is even, so I can just integrate from 0 to infinity. Whenever possible, you want to try to make your life as easy as possible. All right, so this is the same as integrating from 2 to pi, I'm sorry, 2 over pi, integrating from 0 to infinity, arctangent prime of x dx. And I'm trying to make the integral as easy as possible. Can anybody tell me the integral of the arctangent prime? Arctangent, right? Wow, it's really useful that we did that previous slide, right? So we just get 2 over pi, and then we'll have arctangent of infinity minus arctangent of 0. Okay, what angle has a tangent? Okay, so I want to find the angle whose tangent is 0. So what would be the angle whose tangent is 0? I want sine over cosine of that angle to be 0. 0. Now I want to find the angle whose tangent is infinity. So I want sine over cosine to be infinity. What angle would that be? I'm sorry? Pi over 2. I thought I heard something else. 90. I have 2 answers. Which is it, pi over 2 or 90? Pi over 2. What's the derivative of sine of x? The derivative of sine of x is only cosine of x if you use radians. If you use degrees, there's a factor of pi over 180 or 2 pi over 360 because of how things are done. This is one of the reasons why we work in radians, because now the derivative of sine is cosine, the derivative of cosine is minus sine. If you are working in degrees, that is not the case. So as soon as you see a derivative, if you're doing anything with trigonometry with a derivative, you must be working in radians. If you want to then evaluate it in your mind and think degrees, that's fine. But whenever we're writing things down, especially when we're writing down angles, it has to be in radians. And now you can see, why I chose to put in the 1 over pi, because this now integrates to 1. It's a probability distribution. If I didn't put in the 1 over pi, I would see that this integral equals pi, and I would then have to divide by 1 over pi. So this is a probability distribution. Does anybody remember what it's like to be a freshman? So when you meet somebody, what do? You wave hi. Okay, what else do you do? You ask where you're from. What else? What's your major? Interesting name hasn't come on the list yet, but that's okay. There's a bunch of standard questions you ask, right? And after a while, you get to know a little bit about them. Whenever you see a probability distribution, we already know it's a probability distribution. We've checked that. There's certain questions you should ask. What's the first question you should ask of a probability distribution? Well, so in some sense, we've already asked that question by doing this to prove that it's a probability distribution. That's a great question to ask if I give you a function. Are you non-negative and do you somewhat integrate to 1? And once the answer to that is yes, now we're a little bit interested. My son is going to be starting college in the fall. It is very different than when I went to school, where they have all these online things where you start to meet potential roommates. They actually trust people to find who they want to live with. And you start listing different things and you start having conversations. So we're starting to have a conversation with this. We know it's a probability distribution. This is a class 1 probability. We're interested. What's the next question you would want to ask about it? So you could be asking, what type of distribution is it? I mean, we can see a little bit that it's not uniform from looking at this. But what's a general question you might ask about a distribution?
What's its expected value?
What's its expected value? What is your mean? And after that, what might you ask? After you know its mean, what might you ask? What's your standard deviation? And if you're not afraid of looking like a math geek, you might then say, what's your skewness and kurtosis? Right? What's your higher moments? But that's a little much to ask you. But what's your mean? That should be the first question. So looking at this, we want to integrate from minus infinity to infinity of x times 1 over pi, 1 over 1 plus x squared dx. Right, does everybody agree that that's the calculation for the mean? I can pull out the 1 over pi, and I get the integral of x over 1 plus x squared dx. What kind of function is the integrand? Odd. So what is the integral? Does everyone agree that this integral is 0, that it has 0 mean? And now we can work on the standard deviation. Is everybody comfortable with this? This should be a way to fill things in, but I guess I could do like this and just do at least a little bit right now quickly. All right, so I really want to emphasize that this is not good. What's wrong with this? It's an odd function. We're integrating it from minus infinity to infinity. If you wanted to get into a fight with people, you could make a case that it does integrate to 0. But it has to go back to what does it mean to do an improper integral? This is being recorded. I would be careful how I phrase things. I know everybody has wonderful high school calculus teachers who carefully go through all subtleties of improper integrals, and I apologize for boring you with something that you have seen and learned so well. But please bear with me. You've got to be careful whenever you see an infinity in mathematics. What does it mean to integrate from minus infinity to infinity? It should mean no matter how we expand our interval to get all of the real line, we should always get the same result. So it turns out this function is not integrable. So we need, we need the integral from minus infinity to infinity, absolute value of fx of x dx to be finite. And that's not the case here. This function is technically not integrable. We have to be careful how we work with it. And so if the absolute value is finite, everything is okay. Everybody here should have taken multivariable calculus. You should have seen the Fubini theorem about switching the order of integration. I will gamble that most of you have not seen a proof about switching the order of integration. You cannot always switch the order. If the double integral of the absolute value is finite, you can switch. If it's not finite, you may not be able to switch. And if there's interest in this time today, I'll give you an example where you can't switch. You actually get a different answer depending on how you integrate. Over here, we have to be very careful. So for example, consider the limit as a and b go to infinity of the integral from minus a to b of x 1 over pi 1 over 1 plus x squared dx. As a and b go to infinity, that recovers the mean that we're trying to compute. If a equals b, we get 0. Because we can now use the fact that it's an odd function. If a equals b, we're integrating an odd function over a region symmetric about 0, it's going to be 0. Let's consider something else. If b equals twice a, we would have the limit as a goes to infinity, the integral from minus a to 2a of 1 over pi, x 1 over pi, 1 over 1 plus x squared dx. And then this would just be, I can pull out the 1 over pi. And I would have the limit as a goes to infinity, the integral from a to 2a of x over 1 plus x squared dx. Because the integral from minus a to a cancels out. And then I'm left with the integral from a to 2a. If a is really, really large, what does the denominator look like? So for really large x, what does 1 plus x squared look like? Nope. No, what does 1 plus x squared look like if x is large? It looks like x squared. This is equivalent to going to Washington, D.C. and saying, we made a miscalculation in the national debt. It's actually $1 more than you thought. It's a $36 trillion debt. Being off by $1, insignificant. Okay? The 1 plus x squared, it's approximately x squared. What's x over x squared? It's 1 over x. So this is approximately 1 over pi, the limit as a goes to infinity, the integral from a to 2a of 1 over x dx. What function has derivative of 1 over x? Lmx. So this is just equal to 1 over pi, limit as a goes to infinity, the natural log of 2a minus the natural log of a. But what's the natural log of 2a minus the natural log of a? The difference of the logs is divided. So the difference of logs is the log of the quotient. So the log of alpha minus the log of beta is the log of alpha over beta. So this is just 1 over pi, the limit as a goes to infinity, the natural log of 2, which doesn't equal 0. This shows you that I can make the mean be whatever I want. So if it has no mean, what can you tell me about its variance? Has no variance. This distribution has an undefined mean. In some sense, it looks like the mean is 0. And this is where we have the wonderful result, the concept of the median. The median is where half the probability is less, half the probability is greater. This clearly has a median of 0, but it does not have a mean of 0. If you try to do the second moment, so if we try to do the expected value of x squared, that would be the integral from minus infinity to infinity of x squared 1 over pi 1 over 1 plus x squared dx. That's clearly infinity. So even if you want to make arguments that the mean is 0, the standard deviation is supposed to be the expected value of x squared minus the square of the expected value. So even if you're willing to grant that the mean is 0, which I'm not, but even if you do, it still has infinite variance. This is what's known as a fat-tailed distribution. There's a lot of probability far away from the, and I'll say in quotes, the mean or the median. This is a really good distribution to know. One of the greatest dangers is you accidentally sample from a non-representative sample. So imagine we're trying to assess the interest and mathematical ability of Williams students. And we only choose students from people taking 300 level math stat classes. I don't think that would be a representative sample. Now, if we were at MIT or Carnegie Mellon, maybe. But at a school like Williams, probably not. And so you have to be really careful whenever you're doing things. A lot of times when you're testing conjectures, if you only test it with really nice distributions, you might be mistaken as to how general is something. So it's good to have at least one distribution in reserve that has infinite variance. And maybe that doesn't even have a mean. It's a nice probability distribution. So it's a good way to just test and see how robust are some results. Or do I need some extra assumptions? Do I need to say, assume my probability distribution has finite mean and finite variance? Then the following is true. Okay. But this is just a really good distribution to add to your list. Okay. You should have seen this in the book. I'm going to just quickly state it here that you've taken multivariable calculus, you've looked at functions of several variables. We can do the same thing for densities. And so instead of having my density depend on just one input, I could have it depend on n inputs. And it just generalizes as you would expect. I need it to be non-negative, and I need the integral over everything to be 1. And then it just comes down to notation. Instead of writing dx1 through dxn, I might just use things as a product and maybe specify which things I don't have. Now, one of the most important things you can do if you have a probability distribution that depends on several variables is you integrate out everything but one variable. And what you're left with should be a probability distribution. Because the integral over everything equals 1. So if I integrate everything out but 1, I'm left with a function of that one variable. And that should be a probability distribution. So I can focus on just that part. And that's called the marginal density. So if I want the marginal density of xi, I integrate out all the other variables. And that's why in the integration, I have x1, x2, xi minus 1, xi plus 1. I don't integrate out xi. And then the question becomes, when are we able to do this? You should be unhappy over the thought of having to do integration in several variables in terrible spaces. The big hope is that we can reduce things to one-dimensional integrals. If I have to do integrals in general, oh, painful. So you would love things to break down into products. You would love the variables not to depend on each other. And so the random variables are independent if the joint density is equal to the product of the marginal densities. We love this situation because then it's very easy to analyze. Okay. So again, if I integrate out everything but one, I'm left with the marginal. If the joint density is the product of the marginals, then they're independent. Okay. So here is a fun example. And if you want more detail on this, I put the link from the 2015 lecture. So I've got two random variables, x and y. In the first one, I'm giving you the joint density of the pair xy, where x is the number of heads in the first three tosses. So I have 1, 2, 3, 4, 5. So x is the number of heads here, and y is the number of heads in the last two tosses. And I'm assuming these are independent tosses. In the second one on the bottom, I have the joint density of u and v, where u is the number of heads in the first three tosses. And v is the number of heads in the last two tosses. What's the difference? Are these the same problem? Is there any difference between, whoops. Is there any difference between these two? Here, the first, x is the number of heads, y is the number, in the first three, y is the number of heads in the second three of 5 independent tosses. In the second, u is the number of heads in the first three tosses, and v is the number of heads in the second, and in the last two tosses. Is there a difference between these two? Are they the same? If they're the same, then they should have the same joint density function. And they have different joint density functions. Last time I checked, which was last night when I was checking my slides, 1/16 is not 1/32. 3/16 is not 6/32. These are not the same joint densities. Now they have the same marginals. So the way you find a marginal, if I want to find the probability that x equals 0, I sum over all possible values of y. So I would just sum this way, and I would get 1/8. If I want to find the marginal of u, I would sum, and I would get 1/8. And so in both cases, the probability that x equals 0 or u equals 0 is both 1/8. If I want to calculate the probability that x equals 1, I sum over all possible values of y. Now I look at all pairs. I only care about x, so I look at x comma 0, x comma 1, x comma 2. And I see I get 3/8. And when I do the same thing for u equals 1, I sum over all possible values of v. V could be 0, v could be 1, v could be 2. And I also get 3/8. I could also go down. I could say, what's the probability y equals 0? So I have to sum over all the possible values of x. X could be 0, 1, 2, or 3. And if I sum down, I get 1/4. If I do the same thing for v, I get 1/4. So if you check all these numbers, the marginals are the same. So I have two different pairs of random variables. They have the same marginals, but they don't have the same PDF. They don't have the same joint PDF. What's the difference between the two cases? There's one very important difference. Yes. Yes. So notice in the first case, I say they're independent. Imagine I tape the first and the fifth coin together so that they always land both face up or both face down. Or maybe I tape them so that the first coin is face up and the bottom one is face down. I could easily put a dependence on that. And so I'll let you try to figure out what is the dependence here? Can you sniff it out from something like this? At the very least, you can consider this the method of divine inspiration. I thought it would be interesting to look at these numbers. And when I look at these numbers, the top, it's very easy to see this is exactly what you would get if things were independent. If I want to have no heads and no tails, that happens 1/2 times 1/2 times 1/2 times 1/2 times 1/2. If I want one head in the first three, I have 3 choices for that. And if I want one head in the second 2, I have 2 choices for that. That's where the 6 is coming from, 3 times 2. So the top does fall exactly what you would expect if things were independent. The bottom is not what you would expect if things are independent. So you can actually show for the top that they are independent, that the probability of x times the probability of y is the probability of the pair xy. So top is good. For the bottom, there is some relation between the first 3 coins and the last 2. Is there a unique relation? I'm not going to say, but I'll let you see if you can sniff out a possible relation that would work and be consistent with this data. The big take home here is that the marginals are not enough to determine the PDF. You can have several different joint density functions that have the same marginals. And that means the subject can be painful. Okay. So convolutions and the CDF method. So one of the big things we want to do is we want to form new random variables from old random variables. And we want to take simple random variables and combine them to make more complicated ones. And the hope is if we can understand the simple random variables, we can understand these new complicated quantities. I will work for now with continuous random variables because I can then use calculus. You can do this, of course, with discrete random variables and sums. This is also one of the reasons why random variables always take on real numbers, because that way we can add things. I can't add 3 heads and 2 tails. There's no way to combine them. But I can add 3 and 0. What's 3 and 0? 3. Or I could add 3 and -2. What's 3 and -2? 1. So if I have my random variables take on real values, I can combine them, I can add them. If I do things like heads and tails, I can't add them. So let's imagine we have x and y with PDFs f sub x and f sub y. Let's form z to be x plus y with PDF f of z. So the natural question to ask, of course, is what is the PDF? It should somehow depend on f of x and f of y. Is there a nice formula? So let's calculate the cumulative distribution function of z. So this is the probability that big Z is at most little z. But z is x plus y, so this is x plus y is less than or equal to z. Okay. So how would we compute this? Well, I can look at any possible value of x. If I know what x is, can I figure out which values of y will give me a sum that's at most z? Yeah, so this would just be the integral. X goes from -infinity to infinity. And now I would have the probability that I have the value of x. And now I want the probability that y is at most what? So for a given value of x, how large can y be? Yes, z minus x dx. Okay. So this is the integral x goes from minus infinity to infinity, fx of x times the cumulative distribution function of y evaluated at z minus x dx. And so I now have the cumulative distribution function of z. How can I get the PDF if I know the CDF? What do? Derive, I take the derivative. So if I take the derivative, I have to take the derivative of an integral. What's the derivative of an integral? It's a function, but I need to take d by dz of this integral. And so if I knew what the densities were, I could calculate what f of x is, what fy of z minus x is. I could then do the integration, and then I could differentiate with respect to z. I don't know what they are. So if life were good, what would the derivative of an integral be? But what? We said earlier, we had this wonderful rule. The derivative of a sum is the sum of the derivatives. The difference of the logs is the log of the quotient. We have nice relations. If life were good, the derivative of an integral is the same as the integral of the derivative. And that's why you take advanced math classes. So in an advanced math class, they will justify when can you switch the order and say the derivative of an integral is the integral of the derivative. So I'm just going to be honest and say, this is where you need some care. I remember freshman year, the person who became my physics mentor was teaching us a wonderful advanced physics class. We did special relativity, I think, in the first week. We did general relativity, very quickly. It was a tough class. In the math department, they would spend 6 weeks justifying this step. Moving on, we see. Okay, so you have to justify moving the derivative inside. Let's consider it justified. So we will only look at functions where this is justified. If I move the derivative inside, we see clearly that the derivative is not going to hit or do any damage to the f of x because that has no z dependence. So the derivative with respect to z just hits the second thing. What rule do we use to calculate the derivative of fy of z minus x? Chain rule. And notice that this is telling us we're probably doing something right. We know the PDF. We know it's very hard to have an explicit form for the CDF. So when we see the capital F, oh dear Lord, we should be worried about having to do this calculation because we don't have closed form expressions for most antiderivatives. It's wonderful that we take the derivative and we lose the CDF of y and we replace it with the density of y. So when we take the derivative, we get the integral x goes from minus infinity to infinity, fx of x. And now by the chain rule, it would be little fy of z minus x. And now we have to take the derivative of z minus x with respect to x, with respect to z. What's the derivative of z minus x with respect to z? 1. Do we need to put in the 1? No. It's not bad to put it in to remind ourselves that there really is a chain rule going on. This is coming from the chain rule. What's the derivative of z minus x with respect to z? It's just 1. Yes?
How do we differentiate with respect to z of the capital Fy?
Because we're using the chain rule. It's a of b of x. The derivative is a prime at b of z. A of b of z. It's a prime at b of z times b prime of z. So we have the derivative of big F of y. And so really what we're getting here is it's big Fy prime at z minus x times z minus x prime. And this is where the prime notation sucks. Because we have multiple variables going on. What does that prime mean with respect to what variable? It's the derivative with respect to the variable z. X is fixed. So prime means with respect to c. So that's what's going on over here, is we're just using the chain rule to take the derivative of capital F of y at z minus x. And so we first differentiate the capital F of y, and it gives us little f of y, and then we differentiate z minus x. And so we're left with the integral from minus infinity to infinity, fx of x, fy of z minus x dx. If you think about it, this is a very reasonable answer to get. I want to calculate the probability of getting a value of z. Well, if I tell you x takes on the value x, what must y equal if I want to get the value of z? It must be z minus x. That's exactly what we have here. So this is basically saying, go over all possible values of x, and for each x, it has to be associated with z minus x. This is a very reasonable definition. And we call this the convolution. And so we say f star g of z is the integral from minus infinity to infinity of f of x g of z minus x dx. So this is a new operation. You give me two functions, and I can take their convolution. It turns out the convolution has an incredible number of wonderful properties that we will see throughout the semester. Now, properties of the convolution. So f star g of z is the integral from minus infinity to infinity of f of x g of z minus x dx. What if I looked at instead g star f of z? What should the relationship be? Do you think they should be equal? So if I look at g star of f, that's going to be, give myself a little bit more space to work. That would be the integral from minus infinity to infinity of of g of x, f of z minus x dx. Do you think that that's the same as the other? Can you do a change of variable and show that they're the same? So one possibility is to do some algebra. So I strongly encourage you to do the change of variable and show these are the same. Right? I'm going to assume nobody is that eager to do the change of variable and show that they're the same. Who would like a proof by story? All right. So if I give you x plus y, the density is f of x convolved with g of y. If I give you y plus x, what's the density? G of y convolved with f of x. Does it matter what order I add numbers? No, they're the same. So what must be true about the convolutions? They have to be the same. So there is the proof by story. This is actually not as good as the change of variable proof, because the proof by story only works when f and g are probability densities. This proof by change of variable works when f and g are not probability densities. So it's actually better to do that. It's true in greater generality. Do we care? No, because we're only going to use this when we have probability densities. So again, I urge you to do the direct proof by change of variables, just because this is a way for you to practice your integration. And I know for many of you, it has been a long time since you've done integration. I took a very theoretical math class freshman year. If you replaced all of the Arabic numbers with Roman numerals, I don't think we would have noticed. We did very few actual integrations with numbers, which is both good and bad. We got a lot of theory, we didn't get as much practice in doing calculations. Really encourage you, do the change of variables and show that you can do it. If you can't, talk to me, talk to the TAs. All right, so this is one thing that's nice. Can anybody define shampoo mathematics? What do you do with shampoo mathematics? What are the instructions on shampoo? Okay, I've always heard loud the rinse repeat, but something like that. So now that we know the sum of two random variables, what if I gave you three random variables, x1 plus x2 plus x3? Well, I could write that as x1 plus x2 plus x3. So that would be, say, fx1 convolved with fx2, and then you would convolve that with fx3. So we should have a way to write down densities. Do you think this is true for all random variables? So there is a key assumption I'm making about x1 and x2. I'm sorry? Yes. So this is assuming independence. So for example, imagine x is symmetric about 0 and y equals x, y equals negative x. In both cases, y has the same distribution as x. But in the first case, what does x plus y equal? What's the density of x plus y if y equals x? Sorry? Yeah, it's just the random variable 2x. Whereas in the second case, what is x plus y? Identically 0. So you always want to be careful and see what is being assumed. And what we were doing before, when we were writing everything down, we were assuming that x and y were independent. If they're not independent, we would have to use the joint probability density function and integrate over that. And we wouldn't be able to split things. So what we're really doing is we're splitting the probability of x and y. You can see that's where the independence is coming in. So it's very easy to accidentally assume something. If ever I'm doing anything that looks unreasonable, please speak up. I will deliberately try to slip some things past you now and then, but I will always be honest and tell you when I've done it. Okay, I want you to be aware. I want you to be questioning. If I'm going too fast, please slow me down and say, wait a minute, why were you able to do that? And the answer might be, I'm not. I was trying to see if I could get away with it. Sometimes we can justify it. We have to justify switching the derivative and the integral. That's not always possible. Okay. So the next is one of my favorite results, linearity of expectation. So let x1 through xn be random variables, g1, gn be functions such that the expected value of gi of xi exists and is finite. These are very weak assumptions. As soon as something is infinite, it's going to be hard to work with. So think of it as I want the means to be finite. So typically g of x would just be x, but it might be x squared, whatever. And let a1 through an be any real numbers. Then the expected value of the linear combination is the linear combination of the expected values. So again, whenever you can say something in a sentence form and bypass all the mathematics, that's great. At a high level, the expected value of the linear combination is the linear combination of the expected values. Linear algebra is a prereq for this course. I know there might be one or two people who are doing linear algebra as a concurrent class. Hopefully you've seen these ideas of linear combinations. And the idea is we want to break things down into simple pieces and then see how they combine. So in linear algebra, we break things down into different directions, and then we might apply the matrix to each basis vector. The key thing to note is what is not being assumed. We are not assuming the x's are independent. That's why this is such a great theorem. Most things are not independent. And so when you assume independence, you restrict what you can apply this to. So, if x has density f of x, and the expected value of g of x, as we did last time, is just the integral of g of x times the density dx. If g of x equals x, that's the mean. If g of x is x minus mu squared, that's the variance. So this is all just the stuff we did last time. The big thing that's new is the statement of linearity of expectation. And so now we need to prove it. So there's several ways that we could prove it. We could prove it with just two random variables and then say, and you can argue similarly for higher. We could prove it for two and then do parentheses groupings that, I can consider x1 plus x2 a new random variable. And so I can always reduce it to the case of two. Or we could just do directly for n. I think I would much rather do it just for two and keep the notation at a minimum, and then just talk a little bit about how you would handle the general case. So let's consider the expected value of, let's do ax1 plus bx2. This is going to be the integral x1 goes from minus infinity to infinity, the integral x2 goes from minus infinity to infinity, ax1 plus b. Oh, I should really do maybe a1 and a2 rather than a and b. I'll switch it to a1, and then we'll switch these to a2s. Because that'll generalize a little bit nicer. Plus a2 x2. And now I have to I'm calculating the expected value. So I have to put in the density. So it's fx1, x2 of the pair x1, x2, dx1, dx2. That's how I would calculate the expected value. I have to use the joint probability density function. But if you notice, what's hitting it is linear in x1 and x2. What's the integral of a sum? Sum of the integrals. And the integral of a constant is the constant times the integral. So this is really the same as a1 integral x1 equals minus infinity to infinity of x1 integral x2 goes from minus infinity to infinity of f x1 x2 x1 x2 dx1 dx2 plus a2. And now for the other one, I'm going to switch the order of integration. X2 goes from minus infinity to infinity, x2 integral x1 goes from minus infinity to infinity, and then the density fx1 x2 x1 x2 dx1 dx2. And actually for the other one over here, I'm actually doing the x2 integration first. I'm going to put things in brackets to just highlight which ones I'm doing first. Okay, so I'm just using the integral of a sum as the sum of the integrals. I'm using the fact that I can switch the order of integration, and I'm setting it up to make things really nice. I'm integrating x2 goes from minus infinity to infinity. What does this integral give me? So I have my joint density function, and I fix x1, and I integrate over all possible values of x2. What does that integral give me? This is a marginal. This is the definition of the marginal. If you fix one variable, and integrate out everything else, you're left with the marginal of that random variable. This is just the marginal of x1. So the first integral just becomes a1 integral x1 goes from minus infinity to infinity of x1, and then I'll just have the marginal, which is just the density of x1 dx1. And similarly, the second one would just be integrating a2, x2 goes from minus infinity to infinity of x2, and then the marginal of x2, which is just the density of x2. And now what does the first integral equal? Just the expectation of x1, and the second is the expectation of x2. And I'll say that that finishes the proof. We only proved it for the sum of two random variables, but in general, it's either a similar calculation or we could do grouping. And just march down like that, prove it by induction. So again, it's not bad to just put in all the details. I also only did it in the case where the function, g of x was just, a times x. But this would hold more generally. So this is a wonderful result. It is not true for other quantities. The variance of a sum is not the sum of the variances. Does anybody know when the variance of a sum is the sum of the variances? If you had to make a guess of what assumption you would need for the random variables. Independence. If the random variables are independent, then the variance of the sum is the sum of the variances. That's why in some sense variance works better than standard deviation. But in general, the variance of a sum is not the sum of the variances. If you've seen covariances, that's where stuff like this comes into play. Okay. Now, I constantly say you have to be able to answer the who gives a shit, why do we care about this? Let's give an example. Let's look at Bernoulli random variables. Let's say x1 ... xn are tosses of a coin with probability p of heads. So that means each xk is Bernoulli p. Let x be their sum. What kind of random variable is x? So we have a sum of Bernoulli. It's also on the page. Binomial, right? Then it's a binomial with parameters n and p. So then a natural question to ask is, how many heads do you expect to have? If each toss has a probability p of heads, and you toss the coin n times, what do you expect the number of heads to be? So each coin has a probability p of being heads, you toss it n times, what would you guess? NP, right? Well, let's look. The expected value of x1 through xn is just the expected value of x1 plus ... plus the expected value of xn equals n times the expected value of x1 because they all have the same distribution. Because they're all the same, if I can calculate the expected value of x1, that's the same as the expected value of x2. What's the expected value of x1? It's p. So we get 1 with probability p and 0 with probability 1 minus p. So that's just going to be p. Thus, the expected value of x is the expected value of the sum is just n times p. Now, imagine you didn't know linearity of expectation. The expected value of x is just the sum k goes from 0 to n of k times the probability that x equals k. Right? That's how we would calculate the expected value. Okay. So it's the sum k goes from 0 to n of k. What's the probability in a binomial distribution with parameters n and p that we have exactly k heads? So you need to know the binomial density. We have n tosses. I want to have k of the tosses heads. How many ways can I choose k of the tosses to be heads? And choose k. All of the strings are going to have the same probability. If the first coin was heads with a greater probability than the last, I couldn't do this. But because all the strings have the same probability, I just have to calculate the probability of one string and then multiply it by and choose k. So now I know I have exactly k heads. What's the probability that for these fixed coins, each one of them is a head? I have k of them. I want them all to be heads. The probability is p to the k. And then I have the remainder, the n minus k, and that's going to be a 1 minus p to the n minus k. And so you need to figure out what that sum is. There are ways to do this, and we'll see some ways later in the semester. One of them uses this beautiful technique called differentiating identities. But does everyone agree that this is not a very friendly sum to look at? But it's really easy to calculate the expected value of x1. And so the idea is by knowing the expected value of x1, we can very easily figure out what the expected value of x is. Because we can view the binomial process as a bunch of Bernoulli processes and just piece them together. There are a slew of problems where it's very easy to calculate the expected value of the sum. Now, if you want to calculate the variance, then that becomes a little bit harder. I know this is the expected value. I want to know what's the scale of my fluctuations. Sometimes it's not too bad to bound the standard deviation. Look, I can't calculate it exactly, but I can give you a bound. So, okay. Don't have that much time. I'll just end briefly with Fermat primes. And so, everybody agree that 2 is a prime number? How about 3? 5? 17? These are very special numbers. These are numbers of the form 2 to the n plus 1. So when n equals 0, we get 2. When n equals 1, we get 3. When n equals 2, we get 5. When n equals 4, we get 17. So the question becomes, for which values of n is this prime? It turns out that the number of primes less than or equal to x is approximately x over log x. So this is known as the prime number theorem. So we know roughly how many primes there are. So the probability a number is prime is about 1 over log x if the number is of size approximately x. It turns out that in general, if I want this to be a prime, it's got to be of the form 2 to the n plus 1. And so I could try to calculate, do I expect there to be infinitely many Fermat primes? So I'll let xn equal 1 with probability 1 over the log of fn, and 0 with probability 1 minus 1 over the log of fn. So I'm now considering like a random sequence of primes, and I'm trying to estimate, do I think this sequence of numbers, these Fermat primes, this Fermat sequence, do I think this intersects the primes infinitely often? So the expected number for Fermat primes would be the sum of the expected value of each xn, which would be the sum of 1 over the log of 2 to the 2 to the n plus 1, which is approximately the sum of 1 over the log of 2 to the 2 to the n, which is 1 over 2 to the n log 2. Can anybody tell me what the sum of 1 over 2 to the n log 2 is? Finite or infinite? This is a series you should know. Forget the log 2. It's the sum of 1 over 2 to the n. Finite or infinite? Finite. Geometric series. So this simple heuristic predicts that there should only be finitely many primes of the form 2 to the 2 to the n plus 1. It's believed that there's only 5 numbers on the sequence. And so normally we don't consider 2. There's 2 more numbers that are known, and we believe that's it. One of the biggest open problems. And this is the power of expected values, to just get a feel for what the answer should be. All right, so this is a good place to stop. All right.